Hi, it's Ryan. We are starting on to our next section in Applied Mechanics. This is Chapter 6 in your 3A1 textbook, Strength of Materials. There's three major sections to this. So we have the first part where we're looking at some definitions and some basic calculations for stress and strain. We have a second portion where we start looking at beams and the loads that are on beams. And then a third section where we go a little further with beams and we look at the stresses that are built up inside of beams. So this is part one. We're just going to be looking at some definitions and some terms relating to stress and strain. Okay, so when we talk about stress and strain, and we do some evaluations, what we care about are often two things. So one, is something going to bend? So when we have an object and we put it under some sort of stress, is it going to flex or change shape? Okay. The other thing that we care about is an object going to exceed certain limits and break? In this analysis that we do, we really care about how much is the total stress that something's under and is it at risk of breaking. If you go further with your studies, you would start to look at, does something bend? Is it at risk of permanently deforming? So before we start talking about stress, let's backtrack to something we know about. We know about pressure, and pressure is a measurement that we use to talk about forces that are built up inside of liquids and gases. And we measure pressure by seeing a force that's spread out over an area. So our measurement for pressure is force divided by area, and we have units for that. So a Newton per square meter would be our force per area, and that's known as a Pascal. So the capital P-A is our unit for pressure. So if we were to compress a liquid or a gas using some force, then we could create a pressure. I have a little drawing here. So I have a piston that is compressing a fluid, and one thing just to note is that the force seems fairly obvious, so we're applying some force, but sometimes we have some challenges with figuring out what area do we use, because there's lots of areas. There's the area of the whole container, and there's the area of the piston. Okay? So in this case, we would use the piston face as our area that we would use to calculate the pressure. And why? Well, that's the interface between the pressure inside of the fluid and the force that's being applied. So we have that transition that happens across that area. When we talk about stress, stress is the same thing as pressure. Instead of being in a liquid or a gas, it's in a solid. So we still have the same way that we would measure stress, which is we take the force that's being transmitted through something and divide it by the area that it's being transmitted through. Okay. So inside of a solid, what we would consider is a stress as opposed to a pressure. And we would have the same units. So a Pascal would be our same units of stress as we would have with pressure. And you'll note the area. So the area that I've added is not the entire area or the surface area of the object. In this case, the area is the area that the force is passing through. And so it is an area, in this case, that is perpendicular to the force that's pulling outwards. One thing that's going to be really important for us when we're going through the stress and strain section is that when we talk about stresses, well, it's pressure that's built up inside of a solid. And solids are generally pretty strong. And so what that means is that we often have very large values when we're talking about our units inside of our stress and strain section. So we have to be really careful when we're using our calculators and we're working through these units to make sure that we're good about using our SI units and scientific notation. Okay, so we'll do a couple exercises on that. Again, if you have some struggles with this, reach out to me so that we can do some work one-on-one and try to practice these skills. So the first kind of stress that we were going to look at is in the form of compression or tension. Okay, so if we have an object and it's being squeezed or it's being pulled apart, we have either compression or tension. And we can calculate these in the same way, whether it's tension or compression. So we have this symbol sigma, a lowercase sigma, which is our symbol that describes tensile or compressive stresses. And we name them as a bunch of different things: normal stress, axial stress, tensile stress, compressive stress. All of these mean essentially the same thing. And just like pressure, we're measuring them as a force that's applied over an area. So force divided by area. Instead of just calling it the force compared to the area, what I've called it is the normal force. And if we think about what the word normal means, it's not usual. In physics, normal has a very specific definition, and that's a perpendicular force. Okay, so a force that goes at a 90-degree angle to a surface is a normal force. So if we're to backtrack to our little diagram, what we have is a way to determine the stress is the force that's acting, and then the area is perpendicular to the force. So we have a flat surface that is going to be perpendicular to the direction of force. There's one last thing before we move on to our worksheets. If we look at the force that exists in these objects, so I have compressive or tensile stress, one thing that I'm going to need to do is calculate the force. So the question that I often ask is in the top example, is that object being squeezed with a force of 1,000 newtons or 2,000 newtons? So the top object, is it the force, is it 2,000 newtons or is it 1,000 newtons? Same thing at the bottom. Is that under 2,000 newtons of tension or is it under 1,000 newtons of tension? And what you'd find is that the object is under 1,000 newtons of tension. And the reason for that is that in order for me to be able to pull with 1,000, the object has to be able to resist by the same amount. And I don't add that resistance. What I just have is the pull that's pulling apart, and the object itself is resisting. So in these cases, even though I do have two arrows, each with 1,000, one is the applied force and the other is the resistance to allow that force to happen. Okay, let's go to our worksheets and work through and make sure we can answer our questions. Okay, great. So we have our worksheet up, and let's just work through and answer our questions as we go along. So how is pressure calculated? Well, pressure is going to be a force divided by an area. And units would be a Newton per meter squared would be my force and area, and that guy is equivalent to a Pascal. So Pascal is the unit of pressure. What is stress? Well, stress is basically a pressure in a solid. So instead of a liquid or a gas, stress is going to be a pressure in the solid. And how do we calculate it? Well, exact same as my pressure. So my stress is going to be equal to a force per area. And once again, same units, we would have a Pascal or a Newton per meter squared. So we find out that we have some very large potential values. So very unlikely that we're going to have stress that is 20 pascals in an object. More likely that we might have megapascals, so millions of pascals. So we're going to be dealing with large values. What we want to make sure is that we can put some values into our calculator correctly. So let's give those guys a try. Okay, so I have my calculator out, and let's see how we can make sure we're using our calculator effectively here. So if I put in, say I want to add in 6.4 megapascals, I could know that a mega is worth, 1 million. Which means that if I add in my value, yes, I could enter in 6.4 times 1 million. Okay, and I could get my 6.4 million. The other thing that I may be able to do is to put in the mega would be 6.4 times 10 to the exponent 6, knowing that this is also really 10 to the 6th. And I could get my value that way. Okay. That's maybe a better approach than the last one, but I'm going to show you what I think is the best approach. Your calculator is likely to have a button. For instance, mine has an EXP button. Sometimes it may be an E button or others, but let me show you this button. Okay, so what this button does is it replaces the times 10 to the 6th, or times 10 to the exponent. So I would say 6.4 EXP6. And I get 6,400,000. This has some value when I go to my next question. So if I'm multiplying and dividing, the EXP makes it very easy. So 6.4 E6 divided by 8.2 E K is going to be 3, and I can come up with some value. 4, 9. Where you may run into trouble is if you say 6.4 times 10 to the exponent 6 divided by 8.2 times 10 to the exponent 3. And we'll see is that I got quite a different number, so 780 million. So quite a difference. And where that difference came was when I divide it by the 8.2, I want it to make sure that I have everything there in brackets, because everything is being divided, not the 8.2, but also the times 10 to the negative 3 really should be divided. You can really run into problems in this section if you're not careful with your calculator and how you enter things into your calculator. So you either need to be very careful, especially when you're dividing, to use lots of brackets, or else my advice is avoid that and get good at using the EXP button, because it means that you can minimize some of the brackets and some of the work that you're putting into your calculator. So for instance, if we look at the last question, so it would be 8 giga, so 8E9 divided by 2E6 divided by 5E3, and I would get 0.8, and I guess there'd be like a PA still on the bottom. So you can get pretty good with these values, and it makes sense if in this section to make sure you understand how your calculator works and some of the functions that are effective for you. May save you from getting some wrong answers if you're not careful with your scientific notation. Okay, so when we talk about stress, we're going to calculate stress. We have a normal stress is the first stress that we'll calculate. And so, as we said, we had a symbol, okay, which would be a sigma. And that means normal stress. Okay, the two different types of normal stress that we may have would be tension and compression. And how we calculate stress, so stress is going to be a force per area. Your supplement, the symbol that they use for force is P per A. Now, I know they use P quite a bit in mechanics, and I believe what it stands for would be a pull or a push. But P is a pretty popular symbol. We use it for pressure, we use it for power, we use it quite a bit. So I tend to just use force. However, your academic supplement, when you do have your resource that you'll need for your provincial exams, will tell you P. So just be careful that you understand the terminology there. P in this case is a force, and units would be newtons per meter squared, or a Pascal. And normal stress also has a few other names. So we have axial stress, we have tensile stress, we have compressive stress. There's a lot of different terms that are interchangeable with normal stress. And the key thing is the normal is perpendicular. So when we have a force, it's going to be at 90 degrees to that surface area that it's applied upon. And that's what the term normal means. So I have an excerpt from your academic supplement, and just to show, so they've also used another term here, direct stress. Okay, so yet another term for essentially the same thing, the normal stress, the axial stress. And as I said, they've used load per area. It's not pressure. Right? It's P is a force, push or pull. And we can see that in the diagram if we look over here. So they have shown the pressure, or sorry, the pull, pulling outwards, and use that as the P. Okay, so let's look at example 1. A framework tie bar has a diameter of 5 centimeters and is subjected to a tensile load of 100 kilonewtons. What is the stress in the tie? Okay, so let's start out by drawing a little diagram. So we have a round tie rod, okay, and it is 5 centimeters in diameter. So my diameter is equal to 5 centimeters. And it's being pulled by a force of 100 kilonewtons, which means that it also has a resistive force in the opposite direction of 100 kilonewtons, which allows it to have that force, that tensile force inside of the object. Okay, so if we are going to find our stress, that would be a normal stress, and that's going to be a force divided by an area. Force, I'm going to want that to be in newtons. Okay, so my 100 kilonewtons is really equal to 100,000 newtons. Okay. The area becomes a little bit more of a challenge. So let's figure out what area we're talking about. Well, because it's a normal force, I'm going to want an area that is perpendicular to the force. And so in this case, the area that I would have would be a flat surface anywhere inside of that rod that is perpendicular to the force, so acting at 90 degrees to the applied force. And I'm going to have a whole bunch of little slices throughout my object that are potential areas. So I'm going to pick one. If they're all the same area, it doesn't matter where I pick, if this object doesn't change in shape along its length. So if I want to find the area, what I have in this case is a circle. So pi r squared would be the area of a circle. We have a couple of things where we might slip up here, and I'm going to show you a little bit of a shortcut in terms of equations that can be helpful to save a few seconds here and there. So first of all, if we have a circle, all right, and we have a diameter, okay, most objects, if they're solid, we don't really have the ability to measure a radius. We talk about diameters, diameter of a bolt, diameter of a shaft. We don't talk about radiuses. Okay, so even though, yes, our equation for our area of a circle is based off of radius, we don't talk about things having radiuses in real life. So what we talk about would be diameters. And one diameter is equal to 2 radiuses. Or one radius is equal to 1/2 of a diameter is equal to a radius. If I substitute that in the case of a radius, in my area equation, what I would get is area is equal to pi times d by 2 squared. So I've just taken the radius here, which is 1/2 of d, and substituted that in. And if I work it out, what I get is pi d squared upon 4. So you're almost always going to be given diameters in these questions for any round object that you're calculating stresses with. So here's a good version of the area equation to use for diameters. Now, it's not that hard. You could also figure out what your radius is, which is half of your diameter, so 2.5 centimeters. So if you're more comfortable using pi r squared and you're good about doing the conversion from diameter to radius, then that is a great approach as well. So use whichever one you're comfortable with. It's going to lead you to success, whichever one you're most comfortable with. Okay. Before I punch in my value for my area, I just want to make sure that I've got my right units. So my area I want in meters squared, which means that my radius or my diameter I'm going to have in meters. So converting these guys to meters, 100 centimeters in a meter means 0.05 meters or 0.025 meters for my radius. Area is equal to pi times 0.05 meters squared upon 4. Area is going to be equal to pi times 0.05 times 0.05 divided by 4, 1.963 times 10 to the negative 3 meters squared. Okay, so now I have my area. I can put that into my stress equation. So 1.963 times 10 to the negative 3 meters squared. Units look good, so newtons per meter squared. Be careful with your calculator. A exponent on the bottom is always a bit of concern for me. Make sure you're inputting it correctly into your calculator. Use the EXP button or your exponent button, or else make sure you're using brackets if you're using writing out the terminology times 10 to the exponent negative 3. So 100,000 divided by 1.963 e negative 3, and what I get is 59,42435 newtons per meter squared. So sometimes we may simplify that when we're dealing with stresses. So first of all, a newton per meter square is a Pascal. As well, I have certainly the ability to bump back 6 decimal places, and my final answer may end up being 50.9 megapascals would be probably a reasonable answer for a stress on